ProtectForests. This is work that I've done for a conference early this month called KubeCon, but there is a lot of work in here that is very Dagster specific, or it's more about how we use Dagster to do wildfire prevention. We run obviously everything in the cloud on Kubernetes, so the two topics and the two software are very much linked with each other. Well, if you're here, you're at least curious about wildfire and how we use satellite images to prevent wildfire. I have to admit that before joining Overstory, I didn't know much about wildfire preventions, and how wildfire are created and how they spread. These are just a couple of pictures of the LA wildfire that happened early this year in January. This was the second biggest and most destructive wildfire that has ever happened in the history of California. What happened is that back in January 2025, over 29 people died, over 200,000 people got evacuated, 18,000 homes got destroyed, and over 57,000 acres of land burned down. Just to give an idea of what 57,000 acres of land means, this is Amsterdam, and this area is 57,000 acres of land. So it would be like burning this whole area down. So the wildfire was massive, brought a lot of destruction to people, family, businesses, and community. The impact that wildfire have is incredible, and I could have not seen it, and I didn't know about that before joining a company like Overstory. While the case of this wildfire in particular is still in determination, 60% of the most destructive wildfires in California have been caused by faulty or defective power lines. In particular, the biggest wildfire that California ever experienced has been the 2018 Camp Fire, with over 153,000 acres of land burned down, over 3 times this area. And wildfire prevention is not an easy task. It's not easy at all, for a couple of reasons. The first one, power lines are complex. It's like infrastructure, right? It spreads all over a country. Some of it is overground, some of it is underground. Some of it is on public places, some of it is on private property. And these power lines, they need to be reliable. They need to bring electricity to our communities 365 days per year. Whenever they break, their failures are always sudden and very catastrophic. I'm sure you heard just a couple of months ago that one of the sub-power stations of the Heathrow airport caught fire, and for a whole day they had to close the airport down. This caused over 1,000 flights disrupted, over 300,000 passengers affected, and the whole airport to be shut down for 24 hours. And this was just a small sub-power station. Also, our power lines infrastructure is subject to atmospheric agents the whole year around. They are subject to rain, to heat, to cold, to snow. Everything affects them all the time. And they're always, and being infrastructure very vast, is very difficult to inspect. If you think about it, whenever a power line goes over a private properties, the utility company needs to actually ask permission to the landowner to go and inspect these power lines, which is not always easy. So what we do at Overstory is that instead of sending somebody in person to look at those power lines and making sure that everything works correctly and that the maintenance is done properly, we try to solve this problem from the sky. So we use satellite images, aerial images, and machine learning to give actionable items to the energy provider so that they can go and fix problem before the wildfire spreads out. We do that in a relatively simple process that I have simplified in 3 steps. It's much more complex than that, obviously. The first part is that the vegetation data is gathered from remote sensing sources. So we use different satellite providers, we use aerial images, we use some drones as well, and we detect which trees are present in a certain area. What is the height of those trees? What's the condition of the terrain? Is it like a dry terrain? Is there wet terrain, and so on? We combine this information with other infos that is given to us by utility companies, like where poles are placed, how high is the line, what's the tension that is going in that line, and so on. And by combining these 2 information together, what we do is that we create a risk profile so that we can show the utility power line, look, in this place over here, the vegetation got so close to to your power lines that there is a very high risk of wildfire. In this way, the utility provider can go and trim the vegetation before a wildfire spreads out. But let's dig a little bit more into the technical details. So this is how, this is a little bit of context around the wildfire problem. It's not very, it's not a common thing to work on. But let's talk about how we got started. We were a startup of 20 people, and where are we now? When we got started, our stack was extremely simple. We used Jupyter Hub and Kubernetes. That's it. Jupyter Hub, if you're using Jupyter Notebook already, I'm sure you're familiar with Jupyter Notebooks. Jupyter Hub is just a way that allows you to create different Jupyter Notebooks in different servers. So if you need a more powerful machine, you can spawn it very easily into Jupyter Hub. And we use Kubernetes in the cloud because this gives us maximum flexibility. The problem that we have is that some of our workloads require 1 CPU and 4 gigs of memory, and we have other workloads that require 75 CPU and half a terabyte of memory. It's very unpredictable. And this is all due to the fact that we use satellite images. Some of them are even very high resolution, up to 15 centimeter resolution. So as you can imagine, the imagery data that we get is pretty large. So in the beginning, everything was in Jupyter Notebook. This was very straightforward. Data scientists could select a container image that they wanted with the tools that they needed. They could select the machine that they wanted, a more powerful one, a less powerful one, and they would just run their experiments. And that was it. Still, repeatability and tracking as the company was growing, as we got more clients, was a nightmare. And these kind of messages were popping up all the time in our Slack. Does anyone have a copy of this Jupyter notebook? Do you remember which version of Pandas we used a year ago? The whole process was just very manual. The whole delivery process was extremely manual. Every time we got a new client, we needed to have a data scientist or a data engineer take care of that client, that delivery from beginning to end, which was extremely manual and very inefficient. So it was time to automate and to take the next step in our journey. We needed to move away from Jupyter Notebook and find something that would make it a little bit more repeatable. So we basically set for ourselves 2 main objectives. The first one, get rid of Jupyter Notebooks, at least for running those pipelines, right? They're great for exploring data, they're great for playing with data and so on, but they're very difficult to maintain, very difficult to test, and tracking the Jupyter Notebook with Git was pretty fun, a lot of fun. And also we wanted to automate our workflow run. So we needed for our data and workflow orchestrator. But I guess I'm not giving you much of a spoiler, telling you that in our case, Dagster won. So we evaluated a couple of different options. We evaluated Airflow, we evaluated Prefect. We had for a short time, we also used Ergo Workflow, but finally we settled on Dagster. And we liked it for a couple of different reasons. Dagster is open source. There's a very good community. Actually, fun fact, Tim and I met on the Dagster Slack, and we just decided to get this meetup together. We didn't know each other before. We found out that we live in the same city and we work in the same city, and this is how this happened. It allows you to do very fast deployment. So getting started is immediate. You just Dagster dev, Dagster project scaffold, and you're ready to go. You don't need to spend 2 days looking at different blog posts that tell you what's the best structure for your data pipeline project. The maintainers give it to you directly. It's very easy to test locally. It's all about Python modules. And this is something that is very close to my heart since I'm more of a cloud engineer than a data engineer. It has been created and is being built with the cloud in mind, meaning that we are not running things on a virtual machine or a server that is stacked in a wardrobe anymore. We're running in the cloud. We use external services. We use containers very heavy. And when you look at Dagster and the way that's been built, you can really see that their developers have done that with cloud in mind. This is something that you have seen in the previous presentation, so I will not spend too much time on it. In our case, we run everything on Google Cloud. Our user access the Dagster web interface, and there is another pod that is running the Dagster daemon. Basically, these 2 components are the ones that are more on the operator side. So the Dagster web interface shows our users which pipelines are running, which pipes are failing, which pipeline need to be retried, and the Dagster makes sure that everything flows naturally. In the lower part of this image, you see many different deployments or code locations in Dagster terms. Each one of our teams is responsible of one or more code locations, and all of these code locations can be deployed independently with their own environment, with their own schedule, with their own different methods as well, which is pretty nice. This is a feature that I love about Dagster, and this is why I often say that Dagster is really thought with cloud native in mind. I/O managers. With Dagster, what you can do is abstract your storage completely. What does that mean? That it means that if I'm writing my pipeline locally on my laptop, well, Dagster is going to save and retrieve files from my local storage. When I take the same pipeline and then move it into Kubernetes, then what Dagster is doing, without me having to do anything else, it will automatically save and retrieve files from Google Cloud Storage or S3, you name it. And this is amazing, because if you have ever worked with tools like Airflow, this is something that is really complicated with Airflow. Every time you need to put an if, so if I'm running in the cloud, then save it in cloud storage. If I'm running locally, then save it as a file. And this whole abstraction already, like, for me, it was a very big selling point for Dagster. One thing that I was thinking about this when the previous presentation was going on, and I found interesting how we found two different ways of appreciating the world of assets. For me, assets are amazing. It's a great tool that Dagster provides. In my case, what I found out really interesting is that in the past, the data was a couple of different things. It could be either a file, a database, and that was pretty much it. But in the age and the era of cloud, data can mean a lot of different things. It can be a file in Google Cloud Storage, a database, or my Snowflake DB, or maybe a table on BigQuery, or my pipeline that imports data via DLT. Data is not as easy anymore in the age of cloud. Data can mean many different things. And this is why it's so nice with Dagster that we're not focusing anymore on how data is built, but rather on how data relates with each other. Dagster is very good at making this link very explicit, so that I know that this BigQuery table is linked to this file in this way. And this is the power of assets. They make it really easy to visualize those connections. In the pipeline that you see on your left, you have two Airbyte pipelines that are importing data. Then they go through different DBT projects, and finally, I'm running my forecast model just using Python. The link between those pieces of data is explicit, and it's very easily recognizable. Same things on the right. Two file-train pipelines go through DBT, and finally, I'm running my prediction using TensorFlow. Assets make it easy to visualize those things. As we started building more and more using Dagster, there were certain principles and certain tools that we ended up repeating over and over again across different code locations and so on. And so we started building our own internal library that we're using internally at Overstory that helps us to build pipelines and build assets in a way that we like, in a standard way, pretty much. We built a library called Maple. This is why you see op is now a Maple op, like an asset is now a Maple asset. This is just an internal library that wraps around the concept of op, pipeline, and assets, and just adds certain things for us. So as we're running on Kubernetes, what we do in this case is saying, I want this step to run on a node that has a single GPU Tesla MM. I am requiring that this node, I want this node to have at least 32 CPUs available and at least 390 gigabytes of memory available. And this is a very nice feature that's been introduced into Kubernetes not too long ago. We use ephemeral volumes pretty heavily. Those they allow you to attach a volume that is temporary, so it will stay there for the lifetime of the pod. It will be created when the pod gets created, and it will get destroyed when the pod gets destroyed. And this is used by our data scientists and data engineers as scratch space. So whenever this op is executed, a new volume of 150 gigs is attached to it. They can write, do all kind of weird things locally, and then whenever the op is completed, the data is actually pushed to Google Cloud. In the next iteration of Maple that we are planning to rewrite at a certain point, we would like to improve this API. We find that this API is still too much Kubernetes specific. If you've ever used Kubernetes, you know the terms node selector, requests, and so on. We would like to abstract it away from our developers. The problem that we have in general is that, as I was saying before, our workload vary a lot in terms of like the resources that they need. They go from very little to very high resources. And that has been a big challenge in our case, to figure out how to use our resources best without undercommitting. So we don't want to go out of memory, but we don't want to overspend either. One thing that we like about the way Dagster works together with Kubernetes is that whenever we build a pipeline or an asset, we have the possibility of doing it in two different ways. The first one is what we call like single pod, single node. So basically you're saying, I want 4 CPUs, I want 8 gigs of memory, and this is what I need from the beginning to the end of my pipeline. So maybe my pipeline is short, it's just 10 minutes or half an hour. I just reserve 4 CPUs, 8 gigs of mem, I run my steps one after the other in the single container, and that works fine. Or what I can do if I have a more complex pipeline is using the multiple pods, multiple nodes type of pipeline, meaning that every step of my pipeline can be run on a different node with different resources. So maybe the first step just needs 4 CPUs and 8 gigs of memory. The second step, maybe it's very heavy. I need a GPU, 18 gigs of CPUs, and 32 gigs of memory. And then finally, in my last step, I need some ephemeral storage to create the last, the output of my pipeline or my asset. And in this case, I can specify for each one of those steps the resources that I need. In this case, if I have a pipeline that lasts 12 hours and I need the GPU just for a single hour, well, I can just do it in this way. In this way, my GPU is going to be used only for a single hour. I will not waste money and I will not waste resources. What are we doing next? What is the next step now? We like Dagster a lot. Obviously, we've been using it, we were talking before, like I've been using this version 0.13, and I think you said 0.14, something like this, so we're almost there. Pretty much we started at the same time. Pipelines they work fine, and assets work fine. In our case, the problem is that all the clients that we have very different use cases, very different problems. And at times what we found is that our dependency hierarchy gets too complex to model in native Dagster terms. And also another problem that we had is on the observability side. The Dagster user interface is very nice, but when you start to have a lot of pipelines, a lot of code locations, a lot of assets, it becomes overwhelming. It's just a lot of things in your face. And getting aggregated statistics per team or per pipeline or per code location is not as easy as we would like. It is why we decided to build a platform on top. So Dagster will continue to stay our tool of choice to running our workloads and our pipelines, but we decided to build something on top, so that whenever a client comes to us and they're asking us for provide like a risk assessment over a certain area, we will run that through our platform, but then the platform is backed by Dagster. It looks a little bit like this. I tried to put it in a graphical way. So in the lower part, we still have Kubernetes that is running Dagster, of course. On top, we use Cloud Run very heavily at Overstory. In there, we created a couple of different components: starter, router, trigger, and watcher. Basically, what these components do is that they make sure we run our jobs and our assets, and we create our data in a certain order. And whenever things don't go the way we want, they either fix the problem by themselves, or they require an input from a user. Let's put it this way. So these four are just four different Cloud Run services that they communicate with each other using Google PubSub. And the trigger and the watcher, there are two services that either initiate the jobs or materialize assets on Dagster, and the watcher instead monitors the status of those jobs. Since all the messaging happens using Google Cloud PubSub, all the messages are also forwarded to BigQuery. We use OpenTelemetry to export some of those metrics to Google Cloud Metrics, and in this case, this gives us a nice Grafana dashboard that we can use to monitor all these, all this process beginning to end. Remember that one of our delivery can take even weeks, because it seems stupid, but like when there are clouds over a certain area, you're not getting satellite images on that day. You will have to wait the day after, and sometimes it's cloudy for a couple of days in a row, or you need maybe repeated scans. Maybe you need like a certain area scanned, after a couple of days. It's not always, it's not always easy. Nature is very unpredictable. And this is what it looks like right now. So we have different types of deliveries that we've put over here. And basically what we do is that we visualize it in a graphical way using Grafana by using data sources from Google Cloud Monitoring and BigQuery.
Question?
Yeah.
2 slides back. Out of curiosity, what does the watcher look like?
What does the watcher look like?
Yeah.
So all these are microservices. They are all like fast API Python microservices. And what the watcher does is basically looks at the Dagster API. Dagster API are all like GraphQL APIs, so it's very easy to query and get the information that you need. And basically, it just monitors the jobs in Dagster, and whenever a certain event is created, it reports it to the router, which is the one that ultimately makes the decision on which job to run, in which order, and with which configuration.
So that comes out of the box with GCP?
We needed to implement all of this.
Right.
So these 4 microservices, we implemented them ourselves, but they're running in Google Cloud Run, so within GCP,
Thanks.
So you wrote your own control flow to control this inventory?
Yeah, it's a little bit, it sounds a little bit weird. I know. It sounds a little bit weird. I know. It sounds a little bit weird. I understand that. But the main issue for us is that these 2 main issues, we were really struggling with this. So the dependency hierarchies was very complex, and we really didn't find a way to model it in Dagster native language. Also remember that we started using Dagster a while ago, so it could be that in the meanwhile it evolved to a stage where that's possible. And observability. Observability has been a little bit of a pain for us. Dagster does not have a Prometheus exporter, so exporting metrics to Prometheus does not come out of the box. And getting aggregate statistics per team, it's tricky. It can be tricky. And instead, with like OpenTelemetry and with this kind of like PubSub messaging, it becomes very straightforward. Of course, going for Dagster Plus would be an option, but that's not on the table right now for us. Okay, connecting all the pieces and the next steps. This is a message that I screenshotted not too long ago. The platform is something relatively new. We've been working with for the past year and a half or something like this. And like a couple of weeks ago, we got off our first 0-run, 30 minutes rerun of a full pipeline, beginning to end with no failure, which is pretty nice. So it makes us confident this is the right way to go through. And what is next? Well, the target is always to deliver results to our customer as hands-off as possible. It is tricky because in the geospatial world there are a lot of things that can go wrong, but we would like to do that with the help of Dagster and our platform at the same time. So we want to take our platform usage and Dagster automation to the next level over the next months and years to come. We would like more and more to break the one step, one node, one job, one node assumption. Right now, every job or every step that we take an entire node. And that's something that has worked until now, but it has become a little bit more Yeah, tricky. This is the issue. I mean, very often we either experience out of memory error because maybe the input data is much larger than we expect, or just under usage. So a job is reserving like 32 CPUs and it's using 2 of them, which is a waste of money. We haven't played yet with GKE node auto provisioning. Basically, it's a GKE feature that allows you to auto provision node automatically based on Google Cloud Intelligence, something. We haven't tried that out, but that would be interesting. And yeah, avoid as much as possible under provisioning or over provisioning resources. As you can imagine, when you're running a very long pipeline, which takes a lot of resources, you don't want it to go out of memory 15 minutes before the end, and this still happens sometimes. We blame that on a couple of different things. Our monitoring of observability needs to be worked on. Needs to be a little bit better. Needs to be easier for our developers to figure out whenever the resource usage or reservation is not on point. And also we blame it a little bit also on the Maple API, which is too Kubernetes specific for our developers, and that's on our side. We need to build something better, where they just describe how many CPUs they want, how much memory they want, and that's pretty much it. Thank you.